we're looking at some equations. We saw these in earlier examples on the lecture slides. And then we have the equation here. So we have our bromate ion. We've got 5 bromine ions in the balanced equation, but they only play into the rate law once. It's 1. And then the acid is squared. So these are basically to show us that we have to measure the rate law experimentally. And so even though this has 2 N2O5, it really only has one order of dependence on that concentration. And then this last one is complicated. This has a complicated rate law. I'm not sure we're going to do that many that have like a sum in the bottom, but we will look at mechanisms and their rate laws. So that one's much more complicated. Doesn't just come from the stoichiometry. We have to measure it experimentally. And we talked a little bit about using our rate expression. So our rate expression is like our recipe, like how do we measure that rate? The most common mistake on the quiz was for students to write the change in concentration, but then they forgot to divide by the change in time. So we have our rate expression, the change of concentration in time. In this case, it's a reactant, so we're going to make that rate positive. So that negative sign is going to make the rate positive because A is disappearing. And then we have our rate constant times concentration of A to some order. And this is an equation in time. You can think about bringing up that delta T and integrating both sides. And that's how we get the integrated rate law. So it depends, what that function looks like depends on whether the exponent is 0, 1, or 2. So we have our expression. Our rate expression is the left side, the left equal sign. And then on the right we have our rate law, differential rate law. And then we set these equal and take the integral, and that's our integrated rate law, and that's going to show how the concentration changes in time. So if it's 0 order, we get an equation that looks like this. So again, we would think about bringing that dt up here, take the integral, and we end up with a constant. So A at time t disappears at a rate of k times t from whatever initial concentration it started with. So when we plot that, it looks like a straight line that has a slope of minus k. It's a negative slope. Then when we solve for the units on k, we get molarity per second. And you'll see here in the lecture slides, this is in the form of the equation of a line, y equals m times t plus our constant. So there's our y-intercept there. If we have a first order reaction, then we end up with a natural log in our integrated rate law. So we will look at the natural log of the concentration at a given time, and that will disappear, right? So here's the concentration versus time. It's got this curvature, natural log shape. And then when we take the integrated rate law, we now have the form of a line where y is the natural log of our concentration. So it's going to start at natural log of A naught times 0 and decrease linearly from there. So again, we're trying to linearize our data. That way we can make interpolations and extrapolations. The slope on that one is also minus k, and the units on k are 1 over seconds. So those are all handy to have. Ready. Now for second order equation, we again integrate that and we get 1 over A equals KT plus 1 over A naught. So again, it has a shape. It's hard to tell what that is, right? A 1 over X looks kind of similar to a log of X. It's different in the details, but in the general shape, we want something that's linear. So notice that we would take the reciprocal of the concentration in time and plot that versus time to get our straight line. And now the slope is positive. So the slope equals k. And our units on K are 1 over molarity times 1 over seconds. We calculated a bunch of that already. So again, we're plotting a different set of data. And a lot of methods we can use when we have concentration data, we can just pop it into Excel and take a look at which graph is linear. So that's a common approach. All right, I think that's it there. There's a couple of questions and talking about half-lives. Oh, this might be worth looking at. If you are writing down a collection of equations, then you might want to include these half-lives. So what we're doing is we're saying, okay, A at time t is half of what it started out with, half of A naught. And then we plug that in and solve for the t1 half. You can just plug directly into the t1 half formula. So this is for 0 order. So you'd put in that line with your rate law showing that it's just constant. Then you have your integrated rate law, and then you have your half-life expression. So those are handy to have together, like as a cheat sheet, a formula sheet. For the first order, we do the same thing. We plug it into the integrated rate law, solve for t1 half, and we get log 2 over k. So that's pretty familiar if you've worked with things like radioactivity. That's the radioactive half-life. For the second order, same process, plugging in when does that concentration get to half its value. And then here's our equation for the half-life for second order equation. So in this case, it depends on that initial concentration and the K. So those are handy to have tabulated as well. So I think we saw this picture, right? Looking at those half-lives to get shorter and shorter because the concentration changes. So 0, first order, and second order. Notice that these get shorter and shorter for 0 order concentration. These get longer and longer for a second order concentration. It's only for first order that those half-lives are equal. And that was one of the problems that we did in the worksheets. Examples of first order. So if it takes a long time to decay in half, then that means its rate constant is small. If it has a small rate constant, then it's a slow reaction. Okay, so we had left off on page 14 of the worksheets. So we had looked at this one. Oh, but we can just simply plug into the half-life equation. So we want to calculate the T1 half, and that is log of 2, or 0.693 over K. Oh, and let me just plug that in directly. And then calculate the time for it to decompose to 1/8 of its original amount. So that's going to be 3 half-lives, right? So that is going to equal 32.08 hours for 12.5% left. All right, next up. Here we have, this is a first order reaction, and we have our half-life, 35 seconds. And we're gonna, it's just one temperature given. So we're just gonna work at that temperature. In this case, the temperature essentially doesn't come into the calculation because it's not changing. So we look for that first order half-life.
And sorry, Dr. G, real quick, why are we taking the log of 2? Is it because it's a first order?
It's because of the half-life. That falls out right here.
Okay.
Because we're plugging in, so to find the half-life, we're going to let A at time t equal 1/2 A at time 0.
Okay.
And that's a shorthand, right? I could have brackets around all of that. Right, this is really concentration of A at time t. Concentration of A at time 0. And so when we define the half-life, the concentration, half of it's reacted away.
Yes.
So we know that we're saying that A at time t, double A at time t equals A naught, right? Just rearranging this equation.
Okay.
Or plugging that in right here. So I guess I just think of this equals log of 2 over k. So that's the same. Log of 1 over x equals minus the log of x.
Yeah. Okay.
So all of these log rules, a little tricky. Just numerically, it's more digits, right? If you put log of 2, you're going to get more digits in there. But 3 is enough. Yeah, we can leave the rate constant in seconds. That's fine. So calculate the time in minutes. So how many minutes for 95% to decompose? So that means that A at time t is what? There's my concentration at time t. Oh, you know what? I'll just write the general equation down here. Oh, yes. You know what I did? In the general equation, you see I have that natural log of 0 here. When I subtract that, that puts it down here. Do you see what I've done algebraically? So I'm subtracting it on this side, on the right side and the left side. These are going to cancel. And this part is going to equal natural log of AT over A0 equals minus KT. All right, so here these guys cancel. And then the natural log of 0.05, because we have to have that decimal percent. All right, there's my answer, 2.52. So that had a short half-life, but about 35-second half-life, 2.5 minutes to be 95% gone. All right, in the second order rate law, and we just looked at this briefly on the computer in the slides, but now we'll take a look more carefully. So if you think of this as minus dA dt, right, we're going to look at that concentration, A time t minus, so I'm going to integrate, A0 equals integral of Ka squared dt, and that's an A of t, function in time. So I don't want to go into too much of the integral calculus. The nice thing about chemistry is that usually when you have a lot of difficult integrals, they're all given in the front cover of the book. So you don't actually have to manually be doing a lot of the computation. You just have to symbolically know how it works, and then be really careful on your algebra and plugging it in correctly. Here's our second order rate law. We've got y equals mx plus b, so it's in the linear form. We have our a at time t equals kt plus 1 over a naught. And so if we're looking for something that is second order, we know we're going to need our second order rate law. The temperature, again, is given, but doesn't come into the calculation yet. And then this is our initial concentration. So we want to find A at time t equals 2.5 hours. Oh, and now we'll plug in that 2.5 hours. I would try to be careful when you have the reciprocals involved in addition subtraction. Just be really careful with your algebra. And then, oh, per minute. So we need a factor here.
Should we convert hours to minutes first, or is that will that
Yes.
make it harder?
No, either way you want to do it. I'm going to make a little more room here.
Okay.
So I'll go ahead. And we had 2.5 hours, and 1 hour is 60 minutes. There, so I've shown it.
Oh.
All right, now the good thing here is that we have 500. We have matching units, right? And we should. So we have to invert that. Now here we have, we're looking for a time. So how many hours to drop from one concentration to another? So how can we do that one? So we could let this be A at time 0 and this be A at time t. We've got our K value, so then we'll be able to plug everything in.
Sorry, for the A sub t, is it not 0.1504 if you're going to round it off there? Because the next digit was a 7? Or is it?
I would underline there because we have actually, we might even go with just 2 sig figs because of the K value.
Okay.
But yeah, I just stopped. Right, we're not really worrying about sig figs too much because when you go between things like logs, it changes up your sig figs significantly. I'm just going to rewrite this a little bit differently. Just makes it a little bit easier to see if we take away the 4 here. Let's just go with that, 3.2 hours. All right. So half-life for a second order reaction, plugging that in exactly the same way and solving for that T1/2. We get to this expression. We saw that in the slides a bit.
Do you put the filled versions up after you filled them up of these?
Yes. Do you have your Seattle Central email? If you do, you should be able to get into a shared folder. So all of these are, I'm using 0365, but the way it's linked right now, everything that I've done so far is already in there. So I just need to get you that link. Yes, so a bit of algebra. It's kind of fun. I always enjoyed this part. All right, but when it comes down to it, you just have these formulas. Some people get all the way through this without any calculus. So you're really just plugging in and doing a lot of algebra too. But here we're calculating half-lives. Let's keep that on there. Whereas before we were calculating the concentration. So we have the K, and we have the initial concentration, right? So just plug and chug. Oh no, that's 1 over, 1 over. That pops back up on top. That's what I thought at first, and then I second guessed it. 0.0155, and then that's gonna pop the minutes, so minutes on top. And then we'll divide by 60. So half-life, about an hour for that concentration. And because it's the second order, that half-life isn't constant. So this is half-life number 1. Now we're going to calculate half-life number 2 for the remaining sample, and that means that what's our new A naught? This was our original. This is our A naught number. I missed your chat a little while ago. Did you figure out what I was doing? I was just saying, let's work with some easier numbers. 1 over 0.1, let's just call that 10. Yeah, just trying to make it more intuitive so that we could work with those numbers.
How about in this one, going from minutes over 0.0155 to 64?
Yeah, I just did 1 over 0.0155. Does that work for you? Or if you have an x to the minus 1 button, so like on my calculator, I have this little x to the minus 1 button. And so I can just push that and you can just check. You can just click back and forth.
I see. Yeah, I have it too. Thanks.
Yeah, so getting comfortable with the button pushes, like which buttons help you out, can make a major difference in how fast your work goes. So that's a handy one. So we have a new A naught, and that matters because it's in the equation for the half-life. So the second half-life has the same K. And the smaller new concentration. So it slows down. If it's second order, it slows down at the smaller concentrations. Oh yeah, calculate the remaining sample after the 2 samples. All right, so we're gonna look at, so now we have a new A naught.
0.125.
We're gonna use the same K and we're gonna find half-life number 3. Right, so that's gonna basically double again. This is really going to help me tighten up my cursive too. And let me just say because the effective new initial concentration is lower.
Yes.
Does that make sense? Any questions there? Oh my gosh, you guys were way over time. See, I just get so excited. I totally forget. All right, sorry for keeping you over. Feel free to speak up and let me know. And I'll see you tomorrow.
Bye, everybody.
Have a good afternoon.
Quick question, Professor.
Yes.
The prep for tomorrow's lab, do we just follow the instructions in WAMAP for lab number 1?
Yeah, and you don't really need to do anything in the notebook. I would read the materials in advance, and so we'll be working in Excel. If you have Excel, that'd be great if you can pull it up. If you can import that data, sometimes getting that data downloaded into your Excel is the hardest part. So we'll have to figure out how to do that.
Okay, thank you.
Yeah. All right, have a good afternoon.